Yes, hello everyone. This is lecture 17 on discrete mathematics, and in the previous lecture we were discussing properties of composition of function. Okay, so I have given you few properties, and I think you already know f of g is not equal to g of f o f inverse o f is I a when f is function from a to a. When f is a function from a to b, f inverse is from b to a, f o f inverse is ib, f inverse o f is ia. F o g o h is equal to f o g o h, that means associative, and in powers of function it was commutative. Okay, so I have given you idea of all the things. Okay, and next what we have discussed is, so f is 1 1 and g is also 1 1, then f o g is 1 1, and this is one way theorem. I have told you clearly in the previous lecture itself. Okay, so yeah, so I have given you proof also. When f and g are both 1 1, then f o g was 1 1. Similarly, when in the next slide I think I have given you, yeah, so f o g, f is on 2 and g is on 2, then f o g is also on 2, and this was also one way theorem. Okay, this is also one way. Anyway, I will prove it why it is one way and so on, and simply I have proved this thing na. F is on 2, g is on 2, so f o g was on 2. Yes. So now f and g are bijective, then f o g will be bijective. Why? Because from 7 and 8. Sorry, from 6 and 7. From 6 and 7 property, you can think like that. Because 6 was saying 1 1. Okay, 6 was saying f and g are 1 1, f o g is 1 1. 7 is saying f o g, f is on 2, g is on 2, f o g is on 2. So obviously, when we combine them, that means f and g are both 1 1 and on 2, then f o g will be both 1 1 and on 2. Bijection means I think you already know 1 1 and on 2. Okay, 1 1 and on 2. Okay, ninth property is f of g may or may not be defined. I have told you in the previous lecture itself. Okay, yeah, so next property, let me start the next property. I'm jumping to the next slide. You can take the snapshot. Please be active. I have to cover lots and lots of topics in through this class. Let me jump to the next slide now.
Yes, sir.
Okay, so f of g is 1 1, then what can you say about f and g? F of g is 1 1, so f of g is 1 1 means, say this is g and this is f, and they are saying that this is 1 1, f o g is 1 1. Okay, so what can we say about f and g? Okay, so clearly in the previous we have seen this thing na, and f is 1 1, g is 1 1, then f o g is 1 1. So now we want to find the reverse, and I have told you this is one way theorem. F o g is 1 1, then we have to think whether f is 1 1, g is 1 1, both are true or one of them is true. Let me check that. See, since f o g is 1 1, so g cannot be many 1, because if g is many 1, for example 1 2 and 3, and here say 4 5, so like this, if 1 and 2 are mapped to 4 and 3 is mapped to 5, so now here 4 is mapped to say 6 and 5 is mapped to say 7. Okay, yeah, so now if g is not 1 1, like g is many 1, then obviously f of g cannot be 1 1. Are you getting it? G should be 1 1. If g is not 1 1, see this, 1 2 3 and 6 and 7. So 1 is mapped, 1 and 2 both are mapped to 4, and 4 is mapped to 6, so 1 and 2 both mapped to 6. So there is no way out. Are you getting it? So for f of g to be 1 1, g should be 1 1. And forget about f. F can be anything. For example, see this. Let me give you another idea. So the more you think, the more you get. That is the basic scenario of this functions topic. Okay. So for example, if this g and this is f, if g is 1 1, okay, g is 1 1, like this is mapped to this is mapped to this, and say this is mapped to this. Okay, and I have left intentionally one element here, okay, so that it does not become onto. Okay, now say this, for f, if we say like this is mapped to this is mapped to this is mapped to this, and this is also mapped to this. So now clearly you can see f is not 1 1. Why? Because two elements are mapped to one element. F is not 1 1, but g is 1 1. So clearly we can think that f o g will be 1 1. You can check it out yourself. F o g will be 1 1. You can label them 1 2 3, and here 4 5 6 7, and here 8 9 and 10. Okay, let me write it properly, 8 9 and 10. So what will be FOG? So it will be from this set to this set. So 1, 2, 3 and 8, 9 and 10. So 1 is mapped to 4, 4 is mapped to 8. So 1 is mapped to 8, 2 is mapped to 5, 5 is mapped to 9. So 2 is mapped to 9. Okay. And then 3 is mapped to 6, 6 is mapped to 10. So 3 is mapped to 10. Okay. Yeah. So now you can see clearly FOG is 1, 1. FOG is 1, 1. Are you getting it? So the basic thing which you should remember is the more you think, the more you get. That is the basic scenario here. So FOG is 1, 1. Then G should be 1, 1. F may or may not be 1, 1. So this is the proof that why I have said you that this is one-way theorem. Why this is one-way theorem? So FOG is 1, 1. Then G should be 1, 1. F may or may not be 1, 1. Okay. So if it was two-way theorem, then this is true. Then this both should be true, na? But these both are not true. G is 1, 1. This is true, but this may or may not be true. Okay. So forget about F. So you can, if you want to remember this theorem, then you can remember like this. When FOG is 1, 1. So try to remember this thing. So first we will make G and then we will make F. So G should be 1, 1, na? If G is not 1, 1, then forget about it. FOG can never be 1, 1. Okay. When G is many one kind of thing, when G is many one, then FOG will be many one. It can never be 1, 1. Why? Because when multiple elements of G are mapped to one element of here, see this set A, set B, and set C. When multiple elements of set A are mapped to set B, then obviously here this element will be mapped to only one element here, na? Because F is a function. Since F is a function, so this element will be mapped to exactly one element. So directly and indirectly, these two elements will be mapped to this element. That will create problem for us. Okay. So many elements will be mapped to one element. That will create problem. Okay. So for FOG to be 1, 1. G should be 1, 1. F may or may not be 1, 1. So finally the answer will be G is 1, 1. G must be 1, 1. Okay. G must be 1, 1. F may or may not be 1, 1. F may or may not be 1, 1. So I hope you have got it. Please take snapshot. I will jump to the next slide. If anybody is having any doubt, please let me know. Okay. So let me jump to the next slide now. Yes, please tell me. Okay, if you have taken the snapshot, please let me know. Okay. Yeah. So if FOG is onto, then what can you say about FNG? FOG is onto. So see this. So we will try to break this rule. Okay. So FOG na. So first here we will have G and here we will have F. So A, B, and C. Okay. So FOG is onto. So for FOG to be onto, clearly here nothing should be left out. See this. If this is mapped to this is mapped to this. Okay. And say this is mapped to this. Now this element is left blank. So now since there were three elements, so here no matter how many elements you take, all these will be mapped to one of these three. Okay. So now this element will be always left blank. You can never reach here. Are you getting it? You can never reach here. So directly indirectly for FOG to be onto, F should be onto. Okay, G may or may not be onto. For example, here we can have many elements which are left blank. So see this. This is mapped to this. This is mapped to this. Okay, this is mapped to this, and this is also mapped to this. No problem. So now these two elements are left blank. No problem. Okay, but here nothing should be left blank. Are you getting it? See this. For example, I make like this. Now it is guaranteed that it will be what? It will be F is okay. So sorry for that. F will no longer be a function if this element is left out. So we have to map this element to some element like this. For example, I map here. Okay. So now what we can see, F is onto. Okay. And here G is not onto. Okay, and still we will say FOG will be onto. Why FOG will be onto? You can check it out yourself. See this. So 1, 2, 3, 4. Let me label them. 1, 2, 3, 4. Okay, here 5, 6, 7, 8, 9. Here 10, 11, 12, and 13. Okay, so 1, 2, 3, 4. And here 10, 11, 12, 13. Yes, so 1 is mapped to 5, 5 is mapped to 10. Okay, 1 to 10. 2 is mapped to 6, 6 is mapped to 11. Okay, 2 to 11. 3 is mapped to 7, 7 is mapped to 12. Yes. And 4 is mapped to 7, 7 is also mapped to 12. Okay. So yeah. So I think we have done a small mistake here. Let me check this out. 5, 6, 7, 8 and 9. Okay, so yeah, when f is on to f of g to be on to, then what can you say about f and g? Hmm. Uh, okay, let me check this out. F of g is 1 1, then what can you say about f and g? F of g is 1 1. So since f of g is 1 1, then yeah, g should be 1 1. Na? So here f should be on 2. So here f is on 2. Yes, nothing is left out here. And here in case of g, g is not on 2. Hmm. So both are mapped here. So here we have left out one thing. So this is FOG. Okay, so F should be on to na. 1 to 5, 5 to 10, 2 to 6, 6 to 11, 3 to 7, 7 to 12, and 4 to 7, 7 to 13. Okay, so what can we say about F and G for on 2? Just a second. Just a second, okay. I will let me check that out. What is happening here? Mm, mm. So okay, so if FOG is on 2, okay, yeah. So here actually, yeah, we have done a very basic mistake. We have said FOG is on 2, but here itself FOG is not coming on 2. Are you getting it? So I have not taken FOG to be on 2. FOG is not on 2. We have to take FOG to be on 2. Okay, so for FOG to be on 2, we are saying na. Mm, let me clear these things. If FOG is on 2, so if this is logical statement, if FOG is on 2, then what can you say about FNG? So in this example, FOG itself is not on 2. When FOG itself is not on 2, then what can you say about FNG? No comments at all. Okay, so first of all we have to guarantee that FOG should be on 2. Okay, so FOG should be on 2. So now I think FOG is on 2. Okay, see this. Now FOG is on 2. Okay, you can check this out. See, 1 is mapped to 5, 5 is mapped to 10, 2 is mapped to 6, 6 is mapped to 11, 3 is mapped to 7, 7 to 12, and 4 is to 8, 8 to 8 to 13. Okay, so 4 to 13. So I think you have got it. Now we have got FOG to be on 2. Okay, now we can check this out. When FOG is on 2, now we can check. See this, G is not on 2, but F is always on 2. So that's why I was saying if FOG is on 2, then what can I say about F and G? F should be on 2, rather F must be on 2. G may or may not be on 2, may or may not be on 2. These are gate questions, by the way, very important. Okay, make some star over it. So when FOG is on 2, then what can you say about F and G? F must be on 2, G may or may not be on 2. And in the previous slide, if FOG is 1 1, then what can you say about F and G? Then G must be 1 1, but F may or may not be 1 1. Okay, so yeah, let me check that out. You can take snapshot of this, then I will jump to the next slide.
Sir.
Okay, so let me take another slide and I will give you a small hint. So you should remember this thing. FOG is 1 1. if FOG is 1 1, then you have to think about this G. G must be 1 1. FOG is on 2, then think about this F. F must be on 2. Yeah, so you can remember like this: FOG is 1 1, then G must be 1 1. FOG is on 2, then F must be on 2. These two questions are very very important and have been asked in GATE many times. And this is very obvious: when F and G are 1 1, then clearly FOG will be 1 1. No need to worry at all. When F and G are on 2, then clearly FOG is on 2. No need to worry. Okay, and next is when F and G are bijective function, then FOG is bijective. That is for sure. Okay, these three are very very easy and you can easily remember them. The basic thing to remember is this thing. So FOG is 1 1. So try to make the diagram FOG. For FOG you should remember like this. This is FOG. So first here G and here we have F. Okay, so now here we have G and here we have F. So this should be 1 1 now. This should be 1 1. If this is many 1, if multiple elements are mapped here like this, then obviously they will be mapped to one of the element. So when this will be mapped to this element, so obviously these both will be mapped to this element. That will create problem. Are you getting it? This and this will be mapped here in FOG. So obviously it will never be 1 1. Okay, so for FOG to be 1 1, G must be 1 1. For FOG to be on 2, F must be on 2. Why F must be on 2? For example, see this. This is G, this is F, and this is FOG. Now, if this is not on 2, if F is not on 2, let's say this element is left blank, so there is no way out that from here you can reach here. Okay, so from any of these three elements you can never reach here. Okay, so think about that. See, you can think like this. This is city A, city B, and say we have set of cities. Okay, so we have set of cities A, set of cities B, set of cities C's. Okay, so or okay, so from A to B, from A set to B set, we have say some path. Now from B to C we have some path. So now if you want to reach from A to C, then obviously you have to first go to B, na? Then you can reach C. We cannot fly and directly go to C. So first from A we have to go to B, and then from B we can go to C. Now if from B to C there is no path, see this element is left blank, that means from B to C there is no path, then from A to C we can never have a path. Are you getting it? When from B to C there is no path to reach this element, then how you can reach from A to C to this element? Never possible. So this element will always be left blank. Okay, if from in F it is left blank, so obviously from FOG it will be left blank, so it will never be on 2. So for on 2, F must be on 2, that is for sure. Okay, so for FOG to be on 2, F must be on 2. Now I think you have got the point. Okay.
Yes, sir. Yes, sir.
Okay, so let me jump to the next slide. Now we are going to start the next topic. Okay, take the snapshot of this, then I will jump to the next slide.
Okay, sir.
Okay, yeah, now we are going to start counting function. That is also a very very important topic, and many times question have been asked. For example, A is M, number of elements in A is M, number of elements in B is N, then how many functions from A to B? So what we are saying, number of elements in A is M, number of elements in B is N. How many functions? So see this is having how many possibility? This element is having N possibility. Now second element is having how many possibility? N possibility. Third element is also having N possibility. So how many times we will write this N? There are total M elements. So N power M is the answer. Any doubt?
No, sir.
Okay, so please do not by heart this formula. You have to remember this thing. For example, see in GATE exam they can give like this also. A is having N element, B is having N element. So how many possibility? So in your brain try to imagine this thing. A is having N elements. Okay, and B is having M elements. So for first element M possibility, second element M possibility, and so on. So M into M into M, N times. So it comes out to be M power N. Okay, so do not think try to remember this formula by heart. They will change the things. Okay, yes. So small numerical they can ask. Let me see the slide. Yeah, so the small numerical they can ask, for example, set A is having say 10 elements, set B is having say 3 elements, how many functions from A to B? So you will imagine like this: first element of A having 3 possibilities, the second element 3 possibilities, so 3 power 10 is my answer. So simple. Is it okay?
Yes, sir. Yes, sir.
Yeah, take snapshot. I will jump to the next slide.
Okay, sir.
Next, A is having n elements, B is having n elements. How many partial functions from A to B? Partial, see this, we have choice, na? See this. We have m elements here and we have n element here. So first element is having how many possibility? It can map to one of these n and one more possibility. That means it is not mapped to anyone, because in partial function we can have some elements here which are not linked to anybody. That I think I have told you in the previous lectures also. So for first element, how many possibility? N plus 1 possibility. N for these and plus 1 for if it is not mapped to anybody. So directly and directly for first element n plus 1 possibility, second element n plus 1 possibility, dot 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 dot, how many times? M times. So n plus 1 power m.
Yes,
Is it
sir.
okay?
Yes, sir.
Take snapshot. I will jump to the next slide.
Copy, sir.
Next, partial but not total. That is very simple. N plus 1 power m, partial, total n power m. This is my answer. Partial but not total. So let me jump to the next slide. So I have not given you formula questions and all, because formula I have given you, you can make any questions like A is having say 10 elements, B is having say 2 elements, rather 3 elements. So how many partial functions are possible? 3 plus 1 power 10. So you will remember like this: first element 4 possibility, here 3 na, so plus 1, that means it is mapped to no element. That is also possible. So 3 plus 1 power 10, that means 4 power 10 is my answer. Okay. Similarly here you can make a question like this. So set A is having say 10 elements, set B is having say 5 elements. How many partial but not total? So 6 power 10 minus 5 power 10. This is my answer.
Yes,
Okay.
sir.
Yeah, so let me jump to the next slide. So 1 1, how many 1 1 functions are possible? When A is having n element, B is having m elements. So see this. So 1 1 means you cannot map 2 elements to the same element. That is the basic thing. So this element, see total how many elements are here? N, and here we are having m. So this element will be mapped to one of these. So m possibility for the first element. Now for second element, how many possibility are left? See, if this is mapped to this, so total m minus 1 possibilities are left for the second element, because it cannot go here. Okay, so it is having m minus 1 possibility. Next, m minus 2 possibility. Okay, dot 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 dot. How many times you will this will go? So
N1.
and total n terms will be these. So it will be m minus n minus 1. Are you getting it? See this. First,
Yes,
for
sir.
first element here m minus 0. For second element here m minus 1. Third element m minus 2. So total n terms are there. So what will be this? This, see this, m minus 0 to n minus 1, n terms. So this is my simple answer. I think you have got it. Yes. So in shortcut manner, how what we can say? M P N.
Yes, sir.
Okay. So M P N is my answer. Yeah, so I think you already know what is mpn and all. In permutation combination we have done this. So take snapshot. I will jump to the next slide.
Done, sir.
Okay, next, so many one function. So actually I have not given you numerical and all. I think these are simply wastage of time. You can think of any numerical. For example, n is say 10. Okay, b is say you can say 6. Sorry, 6 is not allowed. uh, 10 or 11 you can take. So for example 11 you have taken. So what will be your answer? mpn. So 11 p10 is my answer. Are you getting it? So 11 will be expanded till 10 terms. So 11 into 10 into 9 and so on. So and one more thing is one more point is coming to my mind. See this, when n is 10 and m, this is m na.
Yes, sir.
Yeah, n is 10 and say m is 5. So how many 1 1 functions are possible? You can, by common sense, you can think. See, for forget about 10. 1 2 3 4 5. 5 elements are here and 3 elements are here. So how many 1 1 functions are possible? So for this we have three possibility here, like this and like this. So what about these two? These two cannot be mapped to anybody. So they not possible. So you will say for this scenario 0. 0 1 1 function. We will not say not possible because it is a counting problem. Counting problem means you have to give some number. So number given will be 0. Okay. So for 1 1 function, basic necessity should be length of number of elements in A or size of A should be less than or equal to size of B. Only then functions from 1 1 function from A to B is possible. Otherwise, it is not possible. Are you getting it?
हाँ sir.
Okay, so that is very simple scenario. So final answer will be MPN for this scenario. So for here 10 and here 11, so 11P10 is my answer. Again, I'm saying don't by heart. Better is you in gate exam, if question come like this, you try to imagine the things. Okay, N is 10 and M is 11. So you will think like that. Here we have say 10 elements. Here we are having say 11 elements. So first element, how many possibility? 11 possibility. Second element, 10 possibility, and so on. So 11 into 10 into 9 and so on. Now you can think like that. So I hope you have got it. Please take snapshot. I will jump to the next slide.
Copy sir.
Okay, so how many one? Very very simple. So total minus 1 1. Total is n power m minus mpn. Oh, let me check that out. Yeah. So no, I think. Okay, so if you have any if we have any confusion, we should say like this: A to B. A is having n element, B is having m elements. Okay, so if this is the scenario, then how many functions will be there? M power n. Total functions will be m power n minus 1 1 function. How many 1 1 will be possible? For first element, here it will be having m possibility. Then second m minus 1 and so on. So mpn.
Yes sir.
Any doubt?
No sir.
Okay, so take snapshot. I will jump to the next slide.
Done sir.
Next is how many into functions are possible from A to B. Into the derivation is a bit difficult and bit tricky. So just to save time, I'm not going into that. I'm simply giving you the formula. So you can think like that. Into means what? Some element is left blank. Na? Into, you are getting into this. Okay, so some elements are left blank here. And onto means no element is left blank. So now what we can think. So first element, see this. So first element, okay, so rather we should think in terms of, see this, here we are having 6 elements, 1 2 3 4 5 6, and here we are having say some 8 elements. Okay, so now what we can think from these 6 elements, I will say one of the element is left blank, so I will say 6C1. Are you getting it? So one of the elements, so from 6 you choose one, so 6C1. 61. Now you have you will say it is not mapped. So how many elements are left blank? 5. 5 and here 8. So how many functions will be there from 8 to 5? 5 power 8. Are you getting it? So if this is left blank, so here, so now everything is fit and fine. Okay, so now you can make the function. So 5 power 8. Now now for odd you will add, and for minus, sorry, for even you will subtract. So 6C2 into 4 power 8, then plus 6C3 into 3 power 8. Okay, then minus 6C4 into 2 power 8. Actually its derivation is bit difficult. It is just like derangement type of thing. Are you able to remember derangement? We have done it. So it is just like that only. So 6C1 into 5 power 8 minus 6C2 into 4 power 8, 6C3 into 3 power 8 minus 6C4 into 2 power 8 plus 6C5 into 1 power 8. That's it. So here we will stop. So this is my answer. You can calculate and get the answer. So now similar way we will try to solve this. So here 10 and here 7. So what I will say, I will pick this element B. So starting is difficult. If you are able to start, then you will get it. So 7C1. From 7 you pick one element and you will say it is not mapped. So finally 6 power 10. So from 7 we have deleted one element. So one element is 6 elements are left blank. So 6 to 10. 6 power 10 elements. Okay. Yes. Then plus minus 7C2 into 5 power 10. plus 7c3 into 4 power 10 minus 7c2 into 3 power 10 plus में 7c 7c4 ना 7c4 7c3 4 power 10 7c4 3 power 10 7c5 2 power 10 and then minus 7c6 1 power 10. This is my answer.
Yes, sir.
Okay. Yes, take snapshot. I will jump to the next slide.
Copy, sir.
Okay. Next is A is having 5 elements, B is having 4 elements. So again, 4c1. I'm giving multiple questions so that everything fits in your mind properly. 4c1 into 3 power 5 because 3 elements will be left, na? So 3 power 5. Then it's very easy. Now minus 4c2, you add 1, subtract 1 into 2 power 5. Then plus 4c3, 1 power 5. Answer. Are you getting it? So
Yes,
here
sir.
you add 1 and here you subtract 1. Keep on doing like this. Okay. So an even minus odd plus. So here 3 to 10. Oh, so 10 to 3. So what you will say? 3c1 into 2 power 10. Then minus 3c2 into 1 power 10. And this is my final answer. Okay. Yeah. And if you want intuitive proof, let me give you an idea. Okay. So for example, say A is having 5 and B is having 2. So how many into functions will be there? Let me give you an idea here. Okay. You will get an intuition behind it. Why this formula is working. A is having 5 element, B is having say 2 elements. So what will be your answer? So 2c1 into 1 power 5. That's it. Are you getting it? So 1 power 5 is 1. So 2c1 is nothing but 2 only. So now you will say
Yes.
how sir 2 is coming. So 1, 2, 3, 4, 5. And here only 2 elements are there. So into functions I am doing now. So one of the elements should be left blank. So all the elements, only 2 possibility will be there. All the 5 elements are mapped here. Or second possibility will be 1, 2, 3, 4, 5 and here. So all the elements are mapped to the second element. Okay, so these are only 2 functions possible and formula is also giving us 2 as answer. Is it okay?
Yes, sir. Yes, sir.
Okay, so take snapshot. I will jump to the next slide.
Copy, sir.
Okay, so next is onto. Onto is very easy. So total minus into. Okay. Onto means which is not into to total minus into. So try to remember 1 finding is easy, but many one difficult. So many one will be total minus 1. Okay, similarly into is easy. Into is easy. So into formula I have given you. So onto is difficult. So for onto we will say total minus into. So now here also total minus into. So formula I have given you, so we can put that and get the answer. For example, just for sake of practice, I am giving you how many onto functions from set A is having 8 elements and B is having 5 elements. So we will try to find into first. So starting into 5. So 5c1 into 4 power 8. Then minus 5c2 into 3 power 8 plus 5c3 into 2 power 8, then minus 5c4 into 1 power 8, and here we will stop. When 1 will come, we will stop. So total 5 power 8, 5 power 8 minus this is my answer. Solve and get the answer. Okay.
Yes, sir.
Yeah, take snapshot. I will jump to the next slide.
Copy, sir.
Okay, so next is bijective function. Bijective means 1, 1 and onto. For bijective, I have told you the condition that's number of elements in A and B should be equal. So this is very easy. So for example, here 4 elements and here also 4 elements. So what is the possibility for this element? One of the 4. Okay, so you can map to one of the 4. So like you mapped with this. So now second element, only 3 possibility. You cannot map here. If you map here, it will be many one. And I have told you 1, 1 and onto. Okay, so only 3 possibilities are left. Then say this. Now for this element only 2 possibilities are left and then 1 possibility, so 4 factorial is my answer. So now I think you have got it. For bijective function, if set A is having n elements, B is having only n elements. Okay, m is not possible. Rather, if you want to say nm, then you should say n is equal to m. If n is not equal to m, bijective functions are not possible. Okay, 0 will be the answer. Okay, yeah. So final answer will be n factorial. Okay, so here it should be n only. And if they say, if they want to twist the question, a is having n element, b is having m elements, and n is not equal to m, then how many bijective function? Big 0.
0. Mm.
So permutation function, I think you already know, bijective function on the same set. Okay, so set A is having n elements, and it will be obviously n factorial only, because it is a bijective function on the same set only. Okay. Yes, please take snapshot. I will jump to the next slide.
Done, sir.
Okay, so that's it. Now we are going to start graph theory. Graph theory, last part of your discrete mathematics. So what is graph? Graph is nothing but set of vertices and edges. So we will say G is equal to V comma E. So it is nothing but two tuple. Okay, two tuple V and E. So here, for example, I have given you a graph. So this is your representation, or you can say graphical representation. But in mathematics, how you will represent it? Because we are studying discrete mathematics, so there should be a way to describe this. Okay, so what is the way? For mathematics, mathematics is numbers, or you can say sets. So we will say like this. So what a set is? A, B, C, D, and a set is A, B, B, C, C, D, and A, D. So I have written here in curly brackets. Curly bracket means, see, order does not matter. Okay, so A to B edge we can think, or B to A edge also we can think, because this is like this only. Are you getting it? So that's why I have written in curly brackets. So A, B, B, C, C, D, and A, D. These are the edges. I think you have got it. A, B, B, C, C, D, A, D. That's it.
Yes.
So AD you can write DA and so on. So in mathematics we will say graph is a two tuple vertices and edges. This is your representation, but mathematical representation is this. Okay.
Yes, sir.
Yeah. Take snapshot. I will jump to the next slide.
Perfect, sir.
Okay. So if edges are labeled, then we call it as edge labeled graph. That is very important thing. If edges are labeled, then we call it as edge labeled graph. For example, this is an edge labeled graph because each edge is giving a label. So we will say vertices A, B, C, D. A, B, C, D are the vertices, and edges are E1, E2, E3, E4. So E1, E2, E3, E4. Is it okay?
Yes, sir. In this
Okay,
case, we just write the labels rather mentioning the edge.
Yeah. Okay. Let me jump to the next slide. So graphs are of two types, directed and undirected. Okay, so directed means we will have directions like this. Undirected means there is no direction. Okay, so if you want to represent it mathematically, what we will say, vertices will be A, B, C, D, and edges will be, now you have to label very carefully. So you will say A comma B like this, circular bracket. Circular bracket means it is an ordered pair. So that is from A to B we have an edge, then from B to C we have an edge, then from C to D we have an edge, and from D to A we have an edge. Are you getting it? So edges are labeled, edges will be you can say written like this in the and here we have written like this AB, because there was no direction. Okay, yeah. So an undirected graph is of three types: simple graph, multigraph, pseudograph. So in graph theory, our main concentration will be on undirected graphs only. Okay, directed graph only few topics we will cover, that, don't worry, but undirected graph is very important. Okay, so simple graph, multigraph, and pseudograph. First of all, you should know like this. See, we have A and B vertices. So AB is an edge. So now we can make another edge like this. This is known as parallel edge. Okay, and here also we can make another parallel edge, another parallel edge, another parallel edge, and so on. So we can make like this. Okay, so for A to B, if there is only one edge, then it's okay. If we are having multiple edges like this is a parallel edge. Okay, and this is also parallel edge, and so on. So there should be only one edge. If there are multiple edges, that is parallel edges. So yeah, so simple graph means there is no parallel edges. Parallel edges are not allowed. Self loops are not allowed. Self loop means, say this, A, B, and here like this we have done like this. Okay, this is a self loop. Are you getting it? So from A, starting from A, you are again coming back to A. That is a self loop. Okay, yeah. So self loop is not allowed. So parallel edges and self loop both are not allowed in simple graph. In multigraph, parallel edges are allowed, but self loops are not allowed. But in pseudograph, both are allowed. So most general graph is what? Pseudograph. Most general is pseudograph because there is no restriction. You can have parallel edges, you can have self loop, whatever way you want, you can have. Okay, and most restricted is simple graph. But in graph theory subject, which is related to gate, we will study simple graphs only. We will not unnecessarily dig into multigraph and pseudographs and all. Okay.
So simple
So
graph, you said something.
yeah, simple graph means there is no parallel edges, no self loop like this I have drawn.
You stated something else, sir. Like most general graphs were
Pseudograph.
pseudographs,
Yeah.
and simple graph. You said something.
See, it's most restricted version. Most restricted.
Right, sir. Right, sir. Right, sir.
Because there is lots and lots of restrictions. Now parallel edge is not allowed, self loops not allowed.
Yes, sir.
Okay, so take snapshot. I will jump to the next slide.
Okay.
Okay, so we can think like this: simple graph, and then above it will we have multigraph, and then above it we will have pseudograph. Okay, so every simple graph is multigraph. Yes. Every multigraph is pseudograph. Yes. So from these I can say every simple graph is pseudograph. But vice versa, not true, because there are, see, this is a graph which is pseudograph, but it is not multigraph nor simple graph. Okay, this is a pseudograph which is not multigraph, this and not and not simple graph. I think these are very basic things. Now Venn diagram I have just drawn it. And this is multigraph which is not simple graph. This is simple graph as well as multigraph as well as pseudograph, because here like in Delhi we are standing, that means we are in India, like that. Okay, yeah. So take snapshot. I will jump to the next slide. So now please tell me the types. So this is what, say a self loop is there. Yeah, very good. Pseudograph. This
is simple graph, sir.
Yes, simple graph. So since it is a simple, you should say it is multigraph also, and it is pseudograph also. Yeah. So this is pseudograph, and it is not a multigraph, and it is not a simple graph. What about this?
So that is a multigraph.
Yes, very good. It is a multigraph. Simple graph, no. Pseudograph, yes. Because there were parallel edges, no? That's why.
Yes, sir.
Take snapshot. I will jump to the next slide.
Okay, sir.
And it is simple graph, multigraph, no. Pseudograph, no. So it is. Oh, sorry. What I am doing? Sorry. All the three. Yes, all the three. Yeah, I have tick mark. That's it. Okay. Let me jump to the next slide. So we should note like this: shape and length of edge does not matter. What matters is edge present or not, because we are dealing mathematics. Okay, we are not digging deep into shapes and all. Okay, so like this graph is same as this graph. That means I have you can say converted this edge into curve, and you can make this as a like a spring. Okay, or you can make it like a cloud and so on. It hardly matters, because for all the three graphs, mathematically how you will write graph is set of vertices and edges. So what is the vertices? Vertices are A, B, C, D. Okay, and what are the edges? Edges are A, B, B, C, C, D, and A, D. So for all these graphs you will say the same wording. Are you getting it?
Yes, sir.
So since for all these we are having same representation, so all are same. So for as far as mathematics is concerned, all these four graphs are equivalent. So shape, so try to remember this: shape and length of edge does not matter at all. What matters is edge present or not. Okay, yeah. Take snapshot. I will jump to the next slide.
Yes, sir.
Okay. Next is degree of vertex. Okay, degree of vertex. So degree of vertex is represented by degree V, DGV. Number of edges incident upon V. Okay, how many edges are incident upon V? That is known as degree of V. For example, here A and B, and this edge is E. So degree of A is 1, degree of B is also 1. I have written it. Here degree of C is 2, degree of D is also 2. Clearly you have got it. Number of edges incident upon V. So here this is important for E. What is the degree? 1, 2, and 3, 3, and for F 1. Any doubt? That means self loop. For self loop, uh, it will increase degree by 2.
No, sir.
Self loop degree 2. Uh, Degree of vertex increased by 2. Okay, this is very important point. I will use it after a few slides. I will use this point. Okay, so degree of E will be 3 and F will be 1. Okay, so this is a simple point. Since edge is present between A and B, so they are called adjacent vertices. So this A and B are adjacent vertices. So whenever edge is present between any two vertices, we will call them as adjacent vertices. Okay, so adjacent means edge present between them. Adjacent means edge present. Take snapshot. I will jump to the next slide. Okay. Yeah, so next is, so few terms are coming. So this is a graph given to us. So first term is lone or isolated vertex. Isolated means what? Which is having degree 0. So A is lone or isolated vertex, means degree 0 vertex. Degree 0 vertex. Degree 0 means no edge is there, na? That's why. Pendant vertex. Pendant vertex, like we say in pendant means what? In watches we see. So degree 1. This is pendant. Okay. So F is pendant vertex. So what is F? Degree 1. Degree 1 vertex is pendant vertex. Okay. Another term is order of graph. Order of graph, that is OG. OG is number of vertices in the graph. Number of vertices in G. And here, so we will call it as order G. So here order G is what? Number. Please see this number. So do not say sir A B C D F. No, number. 1 2 3 4 5 6. So order G is 6. Size of graph. Size of graph is number of edges in G. See this number. Okay, this is number. So represented as size G. Size G will be what? So 1 2 3 4 5 6 7 and 8. 8. Okay. 4 are these, 5 6 7 and 8. Total 8 edges are there. Any doubt here?
No, sir.
Okay, take snapshot. I will jump to the next slide.
Okay, sir.
Next is, so degree, another term is degree minimum. Minimum degree, that is represented by delta. So minimum degree here is 0. See this, 0 for the minimum degree. Maximum
Yes.
degree. Maximum degree is represented by capital delta. So what is the degree max here? E. 1 2 3 4 5 and 6. 6. Any doubt here? See this, no? 1 2 3 4, and this is self loop. So 4 plus 2 6.
The self-loop
Degree
will
means,
have two, no?
yeah, degree 2. Yes. So for E, if you are saying E, what is the degree? So forget about this. You simply count the lines. 1 2 3 4 5 and 6. 6 lines are there on this E. That's it.
Okay, sir.
So self loop, you will count like this. So 1 and 2. 2. Okay,
Both
that's why.
have-
So degree max will be 6. Okay, so at another term is coming, if minimum degree is equal to maximum degree, that is equal to constant k, then we will call it as k regular graph. For example, here each and every vertex is having degree 2, so it is 2 regular graph. 2 regular graph. Each and every vertex is having degree 3, so it is 3 regular graph. Is it okay?
Yes, sir.
Okay, take snapshot. I will jump to the next slide.
Yes.
That, yes. So another now theorem is coming, very important. Many questions have been asked in GATE directly or indirectly from this theorem, handshaking theorem. What handshaking theorem is saying? Very simple saying. It is saying sigma, that means sum of degree of all the vertices, that will be twice the number of edges. So sigma degree V, that is equal to twice the number of edges. So sum of degree of all the vertices. Okay, mathematics or in English language, what I will say, sum of degree of all vertices, that is equal to twice the number of edges, is equal to twice the number of edges. Okay, that is the English language. So what is the proof? Proof is very simple. See, every edge increase the degree of one vertex by 2 or two vertices by 1. See this. Uh, if we have drawn an edge, so what this edge is doing? So this edge has increased degree of this vertex by 1 and this vertex by 1. So every edge is increasing the degree of two vertices by 1 or one vertex by 2. That means self loop. Okay, so it has this self loop has increased degree of one vertex by 2 and this edge has increased degree of two vertices by 1. So when I will sum them up, when I will be summing the degree of all the vertices, so 1 plus 1, so 2 will come, but edge is only 1. Here also it will be counted twice and but edge is 1. So obviously when I will sum the degree of all the vertices, it will be twice the number of edges. And doubt here?
Yes, sir.
Okay, so now we can verify this theorem on the previous example. See this. So here, so degree E. Okay, so let me write it. Degree A, then I will write simply A, B, C, D and E. Degree of A is what? 0. Degree of B is what? Degree of B is 3. Degree of C is 2. D is 1, 2, 3, 4. E is 6 and F is 1. Now you sum them up. 6 for 12, 13, 13 and what is what I have done? 3 to 5, 9, 10 and yeah, sorry, 16. 16 is the answer. So 16 is sum of degrees. So sum of degree is 16. So how many edges were there? 8 edges. So 16 divided by 2 is 8. And again I am saying why I have divided by 2. See this edge. It has increased degree of C by 1, B also by 1. See this edge. C degree by 1 and E degree by 1. So when I will sum the degree of all the vertices, then directly indirectly what I have got, I will get twice the number of edges. It's simply common sense. Is any doubt here?
No, sir.
No, sir.
Okay, so yeah, so order of so see the size of graph was 8 and sum of the degree is 16. So it's very simple. Yes, so now we have verified this theorem on the previous example. Let me jump to the next slide. So degree sequence. Degree sequence means degree of each vertex written in ascending or descending order. Okay, degree of each vertex written in ascending or descending order. So write a degree sequence of the graph shown in the previous slide. So this was the graph, na? So I will try to write the degree sequence. Okay, so what is degree sequence? Degree of each vertex we have to write, but it should be in ascending or descending order. So if I write it in ascending order, what will be our answer? What is this? 0 to 0 1 0 1 2 3 4 6 0 1 2 3 4 6. So in ascending order 0 1 2 3 4 6 like this you will write. If you want to write it in descending order 6 4 3 2 1 0 like this. Is it okay? So this is the degree sequence. Now can you predict order and size of the graph from degree sequence? So I want to say in GATE exam they can give like this 6 4 3 2 1 and 0 like this they will give, and now they are asking can you predict the order and size of the graph? Order is very simple. Order means number of vertices. So you will say 1 2 3 4 5 and 6. Order is 6. So simple. Size means number of edges. Number of edges I have told you by handshaking theorem. Sum of degree is twice the number of edges. So edges will be sum of degree divided by 2. So you add them up, you will get 16. 16 divided by 2, 8 is my answer. It's very easy. Take snapshot. I will jump to the next slide.
Done, sir.
Next is this 0 1 2 3 x 6 is the degree sequence and E is 8. Find the value of x. E means edges is 8. Find the value of x. Very simple. So what I will say, sigma degree is equal to twice the number of edges. So sigma degree will be what? 1 plus 2 plus 3 plus x plus 6. That is equal to twice the number of edges. Edges given is 8. So 16. So x comes out to be, you can check that out, 16. So 10, then 69, 11,
12, sir.
9 to 11 to 12. So 4 is the answer. Yes, X is 4. So I think very easy question. Take snapshot. I will jump to the next slide.
Yes, sir. Done, sir.
Hmm. Next, we will study some corollaries of handshaking theorem. Corollary is some extensions. So first is number of vertices of odd degree in any graph is even. But there's very important theorem. Many times it has been asked in GATE. Number of vertices of odd degree in any graph is even. Why? See this. Sum of degree is twice the number of edges. So now, if we say sum of degree means of all the vertices, I am saying it is twice the number of edges. So clearly, it is an even quantity. So sum of degree is even quantity. Are you getting it? Twice the number of edges. Forget about edges. 5, 4, 6, 7, whatever number you keep, twice the number of edges will be even. So directly and indirectly, sum of degree is even quantity. Now degree of all the vertices is even. So these vertices can be of even degree or odd degree. So I will say sum of degree of all the odd degree vertices, sum of degree of all the even degree vertices. Now sum of degree of all the even degree vertices, that will be 100% even. Why? Because you add even any number of time, you will always get an even number.
Even number.
Are you getting it?
Yes,
So
sir.
even numbers, you add even time or odd time, you will get even as the answer. Sum of degree of odd degree vertices, what should be that? Now total sum is even. See this. Now total sum is even, and here also you are having even. Because of this, total sum is even. So now what should be added here to get this? Obviously even you should take here. So how you will get even? Because each and every vertex is of odd degree. So how you will get even as the answer? So clearly you have to take the number of odd degree vertices to be even. Only then you will get here even. That is common sense. Okay. So for example, you add 3 plus 3, you will get even. You add 3 plus 3 plus 3, you will get odd. So if odd degree vertices are added odd number of times, you will get an odd number. But we want even number, so they should be added even number of times. So directly and indirectly, number of vertices of odd degree should be even. Any doubt here?
Understood, sir.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Hmm. Okay, next true false question. Number of vertices of even degree is even. This is true or false?
True, sir.
So number of even degree vertices is even. No, it may be even or odd. This is false. Are you getting it? Is even means it is always true. That means so it should be always true that a number of even degree vertices should be even only. They can be odd also, no? Nobody is stopping us. See this, sum of degree of even degree vertices, it is always even. I have told you, even you can add even number of time or odd number of time, you will always get an even number. Are you getting it? So you think about this logic style. Birds fly. Birds fly means what? Every bird fly. This is a general statement. So if I am saying number of vertices of even degree is even, this is a general statement. That means always even should be there. That means it can never be odd, but it can be odd also. This is a false statement. So number of vertices of even degree is odd. No, again false. It can be even or odd, anything.
Oh, yes,
So
sir.
you
Yes,
should
sir.
say like this: number of vertices of even degree, they can be odd or even. It hardly matters to me. Number of vertices of odd degree is even. Yes, this is true. Number of odd degree is odd. No, false. Because if odd degree is odd, then how you will get sum of degree as even? Handshaking theorem will fail if you get this thing. Okay, so this is true. All these three are false. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. Next is maximum number of edges in simple graph of n vertices is n into n minus 1 by 2. This is again a corollary, second corollary of your handshaking theorem. So why it is true? So number of edges of simple graph of n vertices is n into n minus 1 by 2. So sorry, maximum number of edges, maximum. So what can be the maximum number of edges? See this. If we have 4 vertices, so maximum number of edges can be how many? Okay, we are considering simple graph only. We are not jumping into multi and pseudo and so on. So for simple graph, this is the case. We cannot add any other extra edge here. Okay. Similarly, if you say for 3 vertices, it will be the case. For 2 vertices, it will be the case. Okay. For 5 vertices, what can you say? 1, 2, 3, 4, 5. So you will say like this. Are you getting it? So for 5 you are getting 10 as the answer. For 4 you are having 6. For 3 you are having 3, and for 2 you are having 1. So now if you want to see carefully, here each and every vertex is of degree 4. Are you getting it? So see this for 5. So complete graph. See, we will call this name after few slides. This is known as complete graph. Maximum number of edges means every vertex is adjacent. Na? So see this. This vertex will be adjacent to all the 4 vertices. So degree of this vertex will be 4. This vertex will be adjacent to all the vertices, rest other vertices. So degree will be 4. Here also 4. Here also 4. Here also 4. Are you getting it? So what should be the answer? 4 plus 4 plus 4 plus 4 plus 4. Directly indirectly 5 into 4. That means 20. 20 by 2. That means 10 is the answer. And here we have got 10. Are you getting it? So here, so it will be 3 regular. Okay, so 4 vertices means 3 regular graph. So 4 into 3 divided by 2, 6 is the answer. Okay, yes. So 3. So vertices 3 means 2 regular. So 2. So 3 into 2 divided by 2, 3 is the answer. Here we have got 3. So now I can generalize. If we have n vertices graph, then it will be n minus 1 regular. Are you getting it? Since it is n minus 1 regular, so n minus and n vertices are there. So sum of degree will be what? Sigma degree. Sigma degree, that means sum of degree, it will be n minus 1 plus n minus 1 dot 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 dot. How many times? N times. So it will be n into n minus 1. This is sum of the degree. Now edges is what? Sum of degree by 2. So number of edges will be n into n minus 1 by 2. Hence proved. Is it okay?
Yes, sir.
So I have written here also every vertex is adjacent to every other vertex. So degree of every vertex will be n minus 1. So let me put everything on one slide. Take snapshot. I will jump to the next slide. Done? Okay. Next is k regular graph of order n has nk by 2 edges. I have just proved you. So n minus 1 regular I have done. So k regular graph of order n. Order n means number of vertices. So they will twist the things. Okay, this is the third corollary of your handshaking theorem. Corollary means extension. So k regular graph of order n has nk by 2 edges. So order n means number of vertices. K regular. So every vertex is of degree k. K regular means every vertex is of degree k. So how many vertices are there? N vertices are there. So sigma degree. What will be the sigma degree? Sigma degree will be what? N into k. And how I am getting n into k? So each vertex is of degree k because it is k regular. How many times? N times. So k into n. Sigma degree. So edges will be what? Sigma degree divided by 2. So k into n by 2. This is my answer. It is a gate question, by the way. So graph theory is very, very simple. It is simply common sense. Okay. The more you think, the more you get. That is the basic thing. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. Next. So now handshaking theorem is over. Now we are going to start the second theorem, delta delta theorem. It is your second theorem. What delta delta theorem is saying? So delta, small delta is minimum degree. Capital delta was maximum degree. And 2e by n. What is this 2e by n? That is very simple. See this. Sigma degree was twice the number of edges. So sigma degree means what? If every vertex, say if average. So I think see this. We can have, say, one vertex is of degree say x, another is of degree y, another is of z, and so on. Like this we are having. So if we sum them up, you will get what? Sigma degree. Okay. So totally, if I am saying it is say n vertices are there, so sigma degree, that will be twice the number of edges. So if I divide it by n, and here also divide by n, so sigma degree by n, what is this? So I will say, if I am having say 10 students in my class, one is having say weight x, another is having weight y, another is having weight z, and so on. Average weight, how you will find? You will sum them up and divide by n. So sigma degree divided by n, that is your average degree. So 2e by n, sigma degree is 2e, so 2e by n, that will be average degree. So this is your average. And you already know minimum, average will be greater than or equal to minimum, and it will be less than or equal to maximum. This is known as delta delta theorem. Easy?
Yes, sir.
Okay, so now some questions. So this is very very important. Okay, by the way, no question have been asked in gate till now from this delta delta theorem, but after I think this year or next year, sometimes they will ask question for sure, and it is very basic theorem. So see this, they will ask questions like this. So order of g is 10, delta is 3, then at least how many edges? So as soon as you see at least, at most, you will say okay, this is delta delta theorem question. So you will say, see this delta, so you will apply this part. Okay, so what you will say, delta is less than or equal to 2e by n, so delta is 3, 3 is less than or equal to, order is 10 na? So 2e by 10, so e will be greater than or equal to 15. So edges will be greater than or equal to 15 na? So I will say edges will be at least 15. So how many edges? 15, at least 15. Are you getting it? This is the beauty of mathematics. See this, I have not given you graph, I am just predicting something. Prediction is mathematics type of thing. Order of g and delta is given, so minimum degree is given and number of vertices are given, and they are saying edges how many. So isn't it beautiful thing? I have not drawn graph and I have not given you anything. You are simply predicting that whatever graph you make, this is for sure it will be having at least 15 edges. Okay, less than 15 never possible. Is it okay? Yeah, take snapshot, I will jump to the next slide. Okay,
Okay, sir.
next question is order g is 10, delta is 3, at most how many edges? So again I will say 2e by n, average degree was 2e by n less than or equal to delta, so 2e by n, n is 10 less than or equal to 3, so e will be at most 15. So if maximum degree is 3, then you can have at most 15 edges. You cannot make a graph having maximum degree 3 and vertex is 10 and having 16 or 17 edges. No, not at all possible. You cannot make that graph. That is for sure. Okay. So you can make that graph having at most 15 edges. That is the, you can say, predictions which we can make. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, next is order g is 10, edges is 18, find maximum value of delta and minimum value of delta. So maximum value of small delta and minimum value of big delta. Very very simple. So 2e by n, so delta will be less than or equal to 2e by n, and less than or equal to this. Simple by delta theorem. So delta will be less than or equal to 36 by 10 less than equal to this. So delta will be less than equal to 3.6 greater than equal to this. Now this is important. Please let me know what answer you will you take. So delta will be less than or equal to 3.6. So what can you say? You will take a round off. By doing round off, you will say it is 4 or it will be 3. At most 3. You cannot take 4. Why? Because it is already less than na. So at most 3 is the answer. Are you getting it? And for capital delta, you will say it is greater than or equal to 3.6. So already it is bigger. So you will say it will be at least 4. Are you getting it?
Yes, sir.
So yeah. So take snapshot. I will jump to the next. And why I'm taking this as 3 4, because we are having a graph. So degree cannot be in point na. For any
Okay.
vertex, how it can be 3.6 degree? Not at all possible. Minimum degree cannot be 3.6. So you should take 3 or 4. That was the confusion. So I have given you proof that you should take 3. You cannot take 4. Why? Because it is already less. Since it is already less, so how you can take here 4? Okay, take snapshot. I will jump to the next slide.
Done, sir.
Next, E is 18, delta is 3, N is at least. Very simple. So 2E by N less than or equal to delta. So 2 into 18 divided by n less than equal to 3. So 36 divided by n less than equal to 3. So n will be greater than or equal to 12. So n is at least 12. Okay, and we cannot predict exact answer. No, okay, because if graph is not given, how you will give exact answer? You will say at least 12.
Yes,
Take
sir.
snapshot. I will jump to the next slide. Done. Okay.
Yes, sir. Copy, sir.
Okay. Next is third theorem we are going to study. That is Havel-Hakimi theorem. Third, again very important theorem. Many questions have been asked, but they are saying this theorem tells which degree sequence belong to simple graph. Okay, which degree sequence? Degree sequence. I have told you. You will write ascending or descending order. Okay, degree of vertices written in ascending or descending order. That is degree sequence. So belong to simple graph. See this simple graph. Okay, we are not studying pseudo and all. Simple graph. So how you will find? So the basic idea is, so here we will have 5. I will cut this 5 and I will subtract 1 from each of them. Okay, so it will become 4, 4, 3 and 3 and 2, 5 na. So 1 you will subtract from 5. 1, 2, 3, 4 and 5. Okay, yes. So next I am having 4. So what should I do? Let me take another color. Yeah, so I will cut it 4. I will simply cut it and I will subtract 1 from these 4. So 3, 2. Oops, sorry, I have done yeah. ठीक है. So what we were doing 4, so 3, then it will become 2 and it will become 2 and it will become 1. Are you getting it? So now see, this is now no longer a degree sequence, because what we are getting 3, 2, 2, 1, 3, 2, 2, 1. Are you getting it? See what I have done till now. 5 I will cut it and 1 I will subtract from the next 5 vertices. I have done it. So after doing, I will get 4, 4, 3, 3, 2. Okay, yeah. And I think it was not a degree sequence. Yes, that's why I was getting some problem. Let me write it properly. Yeah, so till here we have done now. After cutting 5, I have subtracted 1 from all the vertices. So what I am getting 4, 4, 3, 3, 2. Now finally what we are having 4, 4, 3, 3, 2 and here 3 we are having. So it is not in descending order. Okay, so degrees, it is no longer a degree sequence. So first you convert it into degree sequence and then we will do the things. So 4, 4, 3, 3, then 3 and then triple 2 and 1. Are you getting it?
So,
Yeah.
why do we stop till that 3? So why don't we just continue to the next 3 also?
For the next what?
After cutting first 5, like ignoring it, then we subtracted 1 from every subsequent number. Why did we stop at 3, sir? The next 3 we did not take.
Okay, because total 5 we have done now. So you are asking question why only 5 are cut? Why next? Why not next?
Why not
I will give the
next?
proof. Yeah, I will give you proof. Don't worry, I will give you proof after doing the steps. Okay, so 4, 4. I think you have got it now. Here we were having 2 and here we were having 3. That was creating problem. So first I have converted into descending order like this. So we have got it. Now what I will say, now I will cut this 4. From the subsequent 4 vertices I will subtract 1. So 3, 2, 2 and 2. Is it okay? So now till now there is degree sequence is proper because everything is in descending order. Now I will cut this 3 and now I will make all these 3 as 1. Now it is not no longer degree sequence. So now I will convert it into this triple 2, 4 ones. Now I will cut this 2 and make these as 1. Now you can see this. Now only ones are left. So how many ones? 1, 2, 3, 4, 5 and 6. 6 ones are left. So you will say it is a simple graph. So finally what you should get, either zeros or ones. So even number of 1. Final answer should be even ones. Even ones, then simple graph. Okay, if you want proof, I will simply say like this. See this. If this is a graph. Okay, so okay, take this. So you will say 3 3 2 2. This is the degree sequence of this graph. 3 3 2 2. Okay, so now what Havel-Hakimi theorem is saying, you cut this 3 and you will subtract 3 from this. So 1 1 or 1 1 1. So 2 1 1 you will get. So directly and directly I want to say you delete this vertex. The moment you delete this vertex, you will delete this edge, you will delete this edge, and this edge. Okay, so what you are having finally, a vertex with degree 2 and vertex with degree 1, vertex with degree 1. This is what Havel-Hakimi theorem is saying. So you delete the vertex which is having the maximum degree after cutting it. So you will subtract 1 1 from the rest vertices. So how many vertices? Obviously degree was 3, so you will subtract 1 1 from these 3 subsequent 3 vertices.
Yes, sir. Understood, sir.
Okay, yeah, that's it. Okay, so let me take the next question. What this question is saying, double 4. So 4 I will cut it and I will subtract 1 1 from 3 here, 2 2 2. Now still it is you can say in degree, still it is a degree sequence. So I will subtract, I will cut it and I will make it 1 1 1. Now it is no longer a degree sequence, so I will make 2 1 2 3 and this. Are you getting it? 3 ones were there and one more and then this 2. I will cut this 2 and cut this, so 0 0. Okay, so what is remaining now? Only even ones are remaining, so it is a simple graph. Okay, yeah, now let me check this. So 4 I will cut it, I will subtract 1 1 from these 3, so 3 2 2 2. Now still it is a degree sequence, so I will cut this 3 and make this 1 1 1. So now what I am having, so now it is no longer degree sequence, so what I will write, double 2 triple 1. I will cut this 2 and 1 and here 0. Now this is no longer a degree sequence, so I will make like this, triple 1 0. Number of ones are odd, so it is not a simple graph.
Awesome.
For this, I will cut this 7. From the next 7 vertices, I will subtract 1. So 5 4 3 2 1 and 0. 1 2 3 4 5 6. But here we were having only 6 vertices. We were not even having 7 vertices. Clearly it is not a simple graph.
Yes, sir.
Okay, this was Havel-Hakimi theorem. Take snapshot. I will jump to the next slide. So this question I've been asked in GATE many times. Okay, they will give you degree sequence and they will ask you to find whether it is a simple graph or not. So very simple scenario. So in graph theory, you have to remember the things, okay? Because if you forget this Havel-Hakimi theorem, you won't be able to answer this type of question in GATE. So graph theory is very simple. The only thing is you have to remember many concepts. There are lots and lots of concepts in graph theory, but it is very simple. Once you know the concept, you will answer it. Very easy.
They
Take
won't
snapshot.
give the question, sir. It is from Havel-Hakimi theorem or something. They won't give in the question.
No. They will simply say, this is a degree sequence. Is this belong to simple graph or not? Or which of the following degree sequence belong to simple graph? They will say like this.
Okay, sir.
Yeah, take snapshot. I will jump to the next slide.
Copy, sir.
So now we are going to start another topic. It is special graph. It is very important. Okay, you can expect one question from this topic. This topic is very big, very huge topic, but many questions have been asked. Okay, and all these special graphs are simple graph only. Okay, so there will be no self loop or there will be no parallel edges. So first is null graph. Null graph is represented by phi of n. So here vertices should be at least 1, but edges are always 0. See, if vertices are also 0, then how will you represent it? So it is no longer a graph. So for graph, at least one vertex is must. Are you getting it? So that's why I have written. So at least one vertex should be there, but edges can be edges should be 0. Edges should be 0. And here n means n is number of vertices. Number of vertices. So phi of 1, phi of 0, does not exist. 0 means 0 vertex. How 0 vertex you will represent? We cannot represent. So 5 0 not allowed. 5 of 1 is allowed. So how 5 of 1 will look like? This. Very simple. 5 of 2 like this. 5 of 3 like this. And I think it is very obvious. You can make it like this, you can make it like this, and so on, whatever way you want. The only thing is 3 dots. 3 dots, 5 of 3. Okay, and edges, no edge should be there. 5 of 4. I think it's wastage of time now, and so on. Okay, take snapshot. I will jump to the next slide.
Copy, sir.
Okay, next, regular graph. What is regular graph? Regular graph, I think I have told you, minimum degree, maximum degree, that is equal to constant k. Zero regular. Zero regular means phi only, phi of n, because every vertex is of degree 0 na. Here see this, every vertex is of degree 0. So 0 regular, this, 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 and so on. So that is phi of n. Phi of n, 0 regular, same. 1 regular. 1 regular means degree 1. Each and every vertex should be of degree 1, like this. Any other way? Yes. Like this. Any other way? Yes. There are multiple ways, and so on. So all these are 1 regular. Any doubt? 2 regular. 2 regular means every vertex is of degree 2. So smallest 2 regular will be this. Okay. Without 3 vertices, you cannot make 2 regular graph. Okay. Next, this. Next, this. So this is a disconnected graph. Okay. This is a single graph only. Are you getting it? This is a graph. This is a graph. This is also a graph. And you can make another graph like this. Okay. You can make another graph like this. All these are 2 regular. Any doubt?
Done, sir. No, sir.
Okay, so 3 regular I have not shown. Okay, so 3 regular. Example of 3 regular like this. Every vertex is of degree 3.
Yes, sir.
Okay, and so on. So that is not required. Okay, so this is regular graph. So now I will tell you some important points. Let me jump to the next slide. Take snapshot.
Done, sir.
So very important points. These has been asked in GATE many times. First, for k regular graph, minimum number of vertices required are k plus 1. For example, see this, for 0 regular, minimum number of vertices was 1. For 1 regular, minimum number of vertices were 2. For 2 regular, minimum number of vertices was 3. For 3 regular, minimum number of vertices is 4. So that is what. For k regular, minimum number of vertices required are k plus 1. In MSQ, they will ask such questions. Which of the following is true, which of the following is false. So if k is odd, the number of vertices must be even. That is for sure. By handshaking theorem. Are you getting it? If k is odd, the number of vertices must be even. For example, 3 regular. For 3 regular, number of vertices must be even. Na? Why? Because 3 regular means what? Every vertex is of degree odd. So number of odd degree vertices in graph is even. I have told you in handshaking theorem, say this.
Yes, sir.
Number of vertices of odd degree in any graph is even. For sure. Okay. So directly indirectly, this is saying this only. So if k is an odd number, the number of vertices must be even. So simple. Regular graph may or may not be connected. That is also obvious. See this. This was connected graph, no doubt. This is disconnected. This is disconnected. Okay. This is disconnected. 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 And so on. So it may or may not be connected. So regular graph may or may not be connected. Very important points. Okay. Take snapshot. I will jump to the next slide.
Done, sir.
Okay. Next is complete graph. Okay. So first we have done null graph. First was null graph. Second was regular graph. Third is complete graph. Complete graph is represented by k of n. So simple graph having maximum number of edges is known as complete graph. There exists edge between every pair of vertex, and hence every pair of vertices are adjacent. I have told you k1. How k1 will look like this. Okay. So I will say, so now apply the definition if you have any doubt. So k1 is this. So you will say maximum number of edges here will be what? Simple graph I am talking. So do not say self loop and all. So 0. And there exists edge between every pair of vertices. Hence every pair of vertices is adjacent. When there is no pair, then how you will check? Okay, that is for sure. So K2, how K2 will look like this. K3, how K3 will look like this. So K4, K4 will be this. K5, how K5 will look like. Okay, so I should tell you the another way of thinking. So K1 is this, K2 is this. For K3 you will make K2. After making K2 you will add one vertex and you will say all are connected. So this is all about K3. How K4? For K4 you will take K3. This is K3. You make another vertex and you will say it will be connected with all of them. All of them connected. So you will get this. For K5, for K5 you will say I will take K4 and I will add one more vertex and it will be connected to all the vertices. This is K5. Okay. Yeah. So like this you can make K6, K7 and so on. So there is this edge between every pair of vertex and hence every pair of vertices adjacent. And I have told you earlier also complete graph Kn, how many edges, n into n minus 1 by 2. Very very important. Many times this has been asked in GATE. And I have proved it by handshaking theorem also.
Yes, sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Okay. So note very very important points for this graph. Kn is n minus 1 regular. I think I have told you previous slides also. K2 is 1 regular, K3 is 2 regular, K4 is 3 regular, K5 is 4 regular. You can check it out yourself. K1 is 0 regular and K1 is nothing but your phi of 1. They will ask like this also. So complete graph of one vertex is same as null graph of one vertex, and that will be same as 0 regular graph. 0 regular graph of one vertex. 0 regular of one vertex. Is it okay? All these are
Yes, sir.
same. Yes, Kn is n minus 1 regular. Every Kn must be connected. Obviously, how you will make complete graph as disconnected? Never, because every vertex is adjacent. When every pair of vertex is adjacent, so you cannot
Yeah.
make isolated vertex and all. Okay, size of Kn, that is nc2 n into n minus 1 by 2. Size means number of edges. Order means number of vertices. Size means number of edges. Basic terms you should know. Take snapshot. I will jump to the next slide.
That's sir.
Okay, next cycle graph. Cycle graph is represented by C of n. So cycle graph is a polygon with n vertices and n edges. Okay, so polygon means connected only. Like this, we make polygons like this, no? So polygons means connected only. So cycle graph is polygon with n vertices and n edges. So vertices and edges are same. So C3 like this, C4 like this, C5 like this, C6 like this, and so on. Okay. So with n vertices and n edges. Okay. So vertices and
And
edges are
same.
so cycle graph. I think you have got it. Two regular. I should say like this. Two regular. So every two regular is cycle graph. No, two regular can be like this also.
Hmm.
This is not a connected graph. But cycle. This is not a cycle graph. Clearly you have got it. This is not a cycle graph. Okay, so two regular and connected. You should say like this. So they will ask questions like this also. So they will try to mingle up the definitions. So what is cycle graph? Cycle graph is two regular as well as connected. So every two regular cycle? No. Okay, yeah. So one way theorem I can make. Cycle graph is two regular. This is one way.
Sir.
But two regular is not cycle. So every cycle is two regular, but every two regular is not cycle.
Hmm.
Okay, take snapshot. I will jump to the next slide.
Done,
Done?
sir. Sir.
Okay. So note cycle graph and cyclic graph and cycle graph are different. Cyclic graph means there exists cycle in it. If there exists a cycle in the graph, it is not a cyclic graph. But cycle graph is different. I think I have told you what is cycle graph. So cyclic graph example can be like this. This is a cyclic graph. Why? Because there is a cycle in it. Okay, A, B, C, D and E. So A, B, C, D is a cycle. Similarly, you can consider this is a cyclic graph because we should need one cycle, but there are many cycles here. Now do not say two cycles. This is also one cycle, pentagon. Okay, and this is one. So there are total three cycles here. Are you able to see them?
Sir.
So A, B, C, B, C, D, E. and A, B, C, D, E. Okay. Yes. Take snapshot. I will jump to the next slide. Okay. Sorry for that. Cn and Kn are same for n is equal to 3. 2 points are left out. Cn and Kn are same for n is equal to 3. So directly and directly I want to say C3 is K3. You already know K3 was this, C3 is this. Both are same. Okay. Cn is 2 regular and it is always connected. I have already told you 2 regular and connected. Yeah. Now take snapshot. I will jump to the next slide.
Done, sir.
Okay. So next we are jumping to wheel graph. What wheel graph is? So okay, let me show you here. So see this. We have a cycle graph. This is C3. Take C3.
Yes.
You make one vertex here and you connect it with all these. These are known as spokes. These are known as spokes. Okay. So another. This is you can say C4. So this is
Yes.
C3, na? This is C4. You take in between one vertex and like this. Okay, this is the wheel graph. Another like this, and so on. So as this number increases, this is C5, na? So as this number increases, I think you have got it. You will get a wheel kind of thing.
Yes, sir.
Yeah, so that's why we are saying it wheel graph. Now see this. Take cycle graph and put one vertex in the center and draw edges between vertex and every other vertex of cycle. Okay, between this vertex and every vertex of cycle, we will get a wheel graph. These edges are known as spokes. I have told you, as number of vertices in cycle increases, more and more it will become wheels, hence name wheel graph. Shortest simple graph, which is a wheel, is having 4 vertices. See this. So this is, we will call it as W4. We will call it as W5. We will call it as W6. Okay. Yeah. Number of edges in Wn is 2 into n minus 1. You can check this out. W4. 2 into 3. Okay. 2 into 4 minus 1. Let me write it properly. 2 into 4 minus 1. So you will get 6. And you can count 6 edges only. Okay. So here also for 5 you will say 5 into 4. Sorry. 2 into 4, 8. Or let me write it properly, 2 into 5 minus 1. So 2 into 4, that is 8. Okay, so why we are getting 8? That is very easy. See, W5, how you have made W5 from C4? So C4 was having 4 edges. Now, and one more vertex you have added and 4 edges you have again added. Na? 4 were the spokes, so total 8 is the answer. Is it okay? For W6, you will take C5. So for C5, 5 edges are there. And when you have added one vertex, 5 spokes will be there. So 10. Okay, that's why I have written number of edges in Wn is 2 into n minus 1. Okay. Yeah. So you can take snapshot of these. This is very, very important point. Take snapshot. I will jump to the next slide.
Done, sir.
Okay, so you can take snapshot of this also. Okay, next. N cubes or hypercube or k dimensional cube. What are these? So it is represented by q of n. See this phi n was your null graph, and this is qn. Qn is n cubes or hypercubes or k dimensional cube. It is represented by qn. Okay, first thing is, see, everywhere wn. So we will write it like this, wn, and here n was vertices. So everywhere n was representing vertices. In the previous slide, see cycle graph Cn. N was what? Number of vertices, C4, C3, and so on. Okay, and here Kn, n was number of vertices. Everywhere n was representing the vertices. Okay, and 0 regular, 2 regular, there was no fixed vertices, so we will not talk about it. And here phi of n was number of vertices. Everywhere n was representing vertices, but here in Qn it will be having 2 power n vertices. This is the exception. Okay, so q of n is having 2 power n vertices and n into n minus 1 by 2 edges. I will prove it, don't worry. Why it is having n into n minus 1 by 2 edges, I will prove it. Okay, so smallest possible is q of 0. So you will say now 0 does not mean 0 vertices. You will say 2 power 0 vertices, that is nothing but one vertex, and one vertex and edges how many? So 1 into 2 power 0, 1 into 1, that is one edge only. Oh sorry, what is n here? N is 0 na. So 0 into 2 power 0, you will get nothing. So answer is 0. Don't worry about it, you will get 0 as answer. So it will be like this. So q0 is this. Are you getting it? So let me write it if you have any doubt. So 0 into 2 power 0 minus 1, 0 into 2 power minus 1, that will be 0 edges, and it will be a single dot. And single dot I think you already know. So q0 will be same as what? Phi of 0. It will, sorry, phi of 1. Phi of 1, it will be same as complete graph of one vertex. Okay, and it will be same as 0 regular with one vertex. Now q of 1. Q of 1 will be having 2 power 1, that is 2. 2 vertices. And how many edges? 1 into 2 power 1 minus 1. What is this? See, for q of n, you are having n into 2 power n minus 1 edges, na? So 1. So 1 into 2 power 1 minus 1, that means 1 edge. So 2 vertices, 1 edge, it will be like this. Q2,
Yes, sir.
2 power 2, that means 4 vertices. Edges, 2 na? So 2 into 2 power 2 minus 1. So it will be 2 into 2, that is 4. It is like this. And what is this? You will say it is K2 also, and it is one regular with 2 vertices. One regular with 2 vertices. Okay, you should know all these things. Okay, how Q2 is looking like? It is looking like C cycle graph of 4 vertices, C4, and it is 2 regular with 4 vertices. 2 regular with 4 vertices. Okay, and what is Q3? 2 power 3, 8 vertices. And how many edges? 3 into 2 power 3 minus 1. 3 into 4, that is 12 edges. 8 vertices, 12 edges. So let me draw it. It will be like this. Okay. So 1, 2, 3, 4, 5, 6, 7, and 8. You can check it out.
Yes, sir.
Okay. Yeah. So it is what? 3 regular. You can check. So 3 regular with 8 vertices. 3 regular with 8 vertices. Q4 very difficult. Q5 very difficult. No need to draw. Okay.
Oh.
If you want, you can Google it out. You will get the idea how it look like. So don't worry, gate will not ask questions from this. So till Q3 it is important, they will ask. So how many edges in Q3, how many edges in Q2, and so on, they will ask. Okay, so now you can say, sir, why edges were this? N into n minus 2, n into 2 power n minus 1. I will simply say Q3 is what? 8 vertices and it is 3 regular, na? So I will, first of all I will say Qn is n regular. That is for sure. See this, Q0 was 0 regular, na? Q0 was 0 regular, Q1 was 1 regular, Q2 was 2 regular, Q3 is 3 regular. Are you getting it, na? 3 regular. So Q1 is n regular. So how many vertices are there in Q1? 2 power n. So if n regular graph, by handshaking theorem, how many you can say edges are there? Nk by 2. Are you getting it? And I have told you like this, k regular with n vertices, it was nk by 2. So n regular, if you have any doubt, you will simply say n regular. I will drive it, don't worry. Qn is n regular, and 2 power n vertices are there. N regular, so means what? Every vertex is of degree n. So n plus n plus n, how many times? Total 2 power n vertices are there. So n into 2 power n is sigma degree. Sigma degree is this. Sigma degree is this. Now edges will be how many? Sigma degree by 2. So n into 2 power n by 2. It comes out to be n into 2 power n minus 1 only. Are you getting it? Yes. So please take snapshot. I will jump to the next slide. If you have any doubt, you can ask me.
Understood, sir.
Okay, so let me jump to the next slide. Okay, so next is bipartite graph. Okay, so what is a bipartite graph? A graph G whose vertices can be divided into two non-empty disjoint sets U and V, such that every edge connects a vertex in U to one in V, and U and V are independent sets. So so you will you will get confused. So let me say like this. So graph whose vertices can be divided into two non-empty, you have to remember this thing, two non-empty disjoint sets. So this and this, like this. So you are having a graph, and for graph you should be able to divide its vertex set into two disjoint sets. Disjoint means nothing should be common between them. Two disjoint sets, you will call first as U, second as V, such that every edge connects to vertex of U to one in V, and you are independent set. So that means independent, I will tell you. You should simply say like this. So you can do like this. Okay, so so edges will connect vertices of this to this. Okay, no edge should be there between this, like this. No edge should be there. Okay, and here U and V are independent set. So I will give you idea what is independent set. So independent set in a graph is a pairwise non-adjacent vertices. Don't worry, you will get it. Don't worry. Pairwise non-adjacent vertices. For example, here in this graph, what is the independent set? D and D. Okay, AC is not an independent. So you just take pairwise non-adjacent vertices. Na AB pair. AB is having edge. AC is having edge. AD is having edge. Okay, BC is having edge. BA. So what is left? Which is not having edge? BD. So BD is an independent set. Here, what is independent set? So a pairwise non-adjacent vertices. So you will say, you will take C, E, A. So A, E, C is an independent set. Pairwise non-adjacent. So see this, A and E, no edge. E and C, no edge. A and C, no edge. Is it okay? So independent set in a graph is pairwise non-adjacent vertices. I think you have got it. Okay.
Yeah, we
so
can't say AF, no, sir.
Come again.
We can't
BDF.
say
We can say
AF. AF.
AF. No.
Sir. Because we have
because
got
edge. We have an edge between them. Okay. So if you say AF and E, no, because A and F is having edge.
Yes, yes.
Okay. So what exactly is bipartite? So bipartite means, now I will explain here itself. I will explain. So bipartite is saying a graph is whose vertices are divided into two non-empty disjoint sets U and V. So you will take non-adjacent vertices. Okay, so CE, ACE. So you will take like this, ACE. Okay, and here what will be left out? BDF, BDF. So ACE, BDF. So now you say B through C edge is there. Okay, yeah, A to F, A to F, E to D. Okay, and A to E, A to A to F, and A to B. Yes, A to B. Yes, A to B. Okay, and then C to B, and another C to D. Okay, E to D and E to F. Okay, so every edge, now read the definition, you will get it. A graph G whose vertices can be divided into two non-empty disjoint sets U and V, this is U, this is V, such that every edge connects a vertex in U to one vertex in V. So every edge is connecting from E to U, sorry, U to V or V to U, one and the same thing only. That means there is no edge between this, between U. That means A to C, A to E, there should be no edge. Okay, so and this is written here, such that every edge connects vertex U to one vertex in V. U and V are independent sets. Okay, so U and V are independent. No edge is there between them. So bipartite means what? Bi means two. So you partite means you have divided it into two parts. So a vertex set of a graph is divided into two parts. These two parts are independent sets, and they should be non-empty. They should be non-empty. Okay, and every edge should be between these two only. Are you getting it? So a vertex set should be divided into two parts, and every edge should be between these only. No edge between them. Yeah, any doubt?
Yeah, sir. The last term,
Uh,
that is U and V are independent sets. Here in the below example, bottom left corner, sir.
mm-hmm.
This example, yeah, U and V are independent sets.
Yes.
Just because like we have considered U and V as the independent sets, and there in the example what they have given A, B, C, D, and AC is connected, D and B are not. There also we have written independent sets.
Where? Here.
ऊपर उसके
Yes, ये इधर.
हाँ sir, here only sir, the red color rectangle with the diagonal.
This.
In the independent set explanation, sir.
This part.
The BD considered as independent set.
Yes. BD is independent.
I got confusion with that, and UV are independent sets in the black ink definition.
Yeah. So U and V are independent set. Now, so U is independent and V is also independent. Both should be independent set. That is the scenario. So here I have explained you what exactly independent set means. Independent set means pairwise non-adjacent. So B and D here, they are independent set. They are making an independent set. Why? Because they are non-adjacent. Okay. So here I have just explained you what exactly do you mean by independent set.
Okay.
Okay. So in definition, we were saying now U is U to every edge connects vertex in U to one in V, and U and V are independent set. So what do you mean by independent set? I have explained you here. So I have given you example. Example 1, example 2. Two examples to show what exactly is independent set.
Done, sir.
Okay. Yeah. And now I have proven you why this is a bipartite graph. Why this is a bipartite graph? Because I can divide the vertex set into two disjoint, non-empty, independent sets. Okay.
Yes,
I have divided its vertex set into two non-empty, disjoint, independent sets. That's why it is bipartite graph. Now please answer this. Is it a bipartite graph? So
yes, sir.
to make how it is bipartite?
Even we have divided here also with the
so divide this vertex set. 4 vertices are there into two disjoint, non-empty, independent sets. Two sets you have to make. These two sets should be non-empty, and they should be independent. So how you will make it? Independent set is only BD.
Yes.
If you put here AC, no idea, no way. Why? Because
Right.
AC is having an edge. Any other way? So in A, can I extend it after BD? I cannot. Can I put here A? No, because A and B are connected. Now can I put here what is left out? C. Can I put here C? No, because BC is having edge.
Connected. Yes,
Yeah. Yes. So only 2 I can keep here. Now here I cannot keep 2. Rest 2. What were the rest 2? AC. I cannot put.
Yes, sir.
Okay. Now if you say only A, if you keep only A, forget about C. No, we cannot do it, because how you will adjust C? No way out.
sir.
Okay, so it is not a bipartite graph. Don't worry.
Done.
I will tell you a very beautiful shortcut, and that is theorem also. How you will check in GATE exam whether it is bipartite or not. Don't worry. I will tell you. Take snapshot. I will jump to the next slide.
Copy, sir. Sir.
Okay. Yes. So next is how to check. See this only. So I have just shown you here U and V, and they should be independent and so on. Now how to check graph is bipartite or not. So this is a bipartite graph. I have just told you. So you how you will check in GATE exam? You have to take independent set. That means non-adjacent. AEC, and next was BDF, and we have drawn it. We have checked this out. Yes, this is bipartite. Is it bipartite? So try to take non-adjacent. So A, B, C, D, and E. Okay, take biggest set. A is non-adjacent to E. Okay, E, C, and D. So E and C you can take. Yes, E and C you can take, but D you cannot take, because the moment you take D, E, E, D will be connected. Okay, A, E, C is independent. Are you getting it?
Sir.
Next is BD. This is also independent. Okay, so now our game is over. So I will say A to B edge is there. Okay, and then B to C is there. B to C is there. B to E is there. Okay, and then D to C is there.
And
D to E is there. That's it. So we have divided it. It is a bipartite.
Sir.
Okay, now this checking is really very difficult, because many edges and so on. It will create a big problem for us. So what is the shortcut? Shortcut is no odd length cycle. No odd length cycle. Here we are having an odd length cycle. Cross it. It is not bipartite. There is no odd length cycle anywhere. Take it. It is bipartite. So bipartite. This is a GATE question they have asked many times. This question has been asked in GATE many times. Okay. So bipartite, if and only both ways, no odd length cycle. So if you remember this theorem, you will be able to answer in GATE in 10 to 20 seconds. But if you do not remember this theorem, you will keep on applying the definition and you will not get the answer. So I am telling you, so many things you have to remember in graph theory. Okay, there are lots and lots of theorems you have to remember. If you try to remember them, you will get the answer. And how you will remember them? Keep on revising the thing again and again, and try to solve more and more questions of GATE. You will get the clarity. Okay, so no odd length cycle, that means bipartite. Take snapshot. I will jump to the next slide.
Yes,
okay, yeah, and if you want to prove, then it is very easy. See this. If you have A, B, and C, this is an odd length cycle, a triangle. So so how you will make it two disjoint sets. So if you take here A, now here you have to take BC. So not at all possible. Yes, by common sense we can think. Okay, that is the intuitive proof. Okay, this is intuitive proof. Take snapshot. I will jump to the next slide. Okay. Next, smallest possible bipartite graph will have two vertices. That is very, very obvious. And what will be that? This. And in fact, we can take this also. This is also bipartite. This is what? Phi 2. Null graph of two vertices. It is a bipartite. Why? You simply say A and B. So this is A and this is B. You have divided. Definition is saying what? You should be able to divide the vertex set into two disjoint, non-empty, independent set. So we have divided. That's it. Game over. Okay, every edge should connect from U to V. There is no edge, no problem. Okay, so phi 2 is bipartite. Similarly, this is what? K2. K2 is bipartite. Okay, and this is also Q1. Try to remember all the things. K2, Q1, one are the same thing. You can take it as AB. And this is also bipartite. This is phi 2. Phi 2 is also bipartite. So smallest possible bipartite graph will have two vertices. How you will make by one vertex? If you want to take this graph, how it will be bipartite? You have to make two non-empty disjoint sets. Non-empty. I see this. The word was non-empty. So obviously, when one vertex is there, so how you will make it bipartite? Never possible. So minimum two vertices. Very basic. See, are you able to predict it? MSQ type of question. MSQ many times they will ask these questions. Okay, next. It may be connected or disconnected, like phi of n for all n greater than or equal to 2 is bipartite. That is very obvious. Phi 2 is bipartite, phi 3, phi 4, phi 5 and so on. Every will be bipartite. I have shown you like this. Phi of n for all n greater than 2 is equal to bipartite. Okay, so it may be connected or it may be disconnected. They will ask direct question. Every bipartite graph is connected. No. Every bipartite graph is disconnected. No. There is no connection at all. Bipartite graph may be connected or disconnected. It hardly matters to me. Is it okay?
Yes, sir.
So it may be connected or disconnected. And I think it is very obvious. Phi 3 will be bipartite. Why? Because you have made this. So A, B and C. So it's your choice. Here you take A, B or you take here C and so on. Many ways to divide the vertex set into two disjoint non-empty independent sets. Okay. Yeah.
Yes, yes.
Next. Cn is bipartite if and only if n is even. That is very obvious. Okay. Cn is cycle graph. So C3. How C3 was looking? Like this. Clearly it is an odd length cycle. So it is never be bipartite. C4, yes, it will be bipartite. C5, how C5 will look like? C5 will be like this. It is not a bipartite. Okay, C6, I think I have just shown you. C6 hexagon, it was bipartite. Okay, we have proven it properly. Yes, is it okay now? Next, Kn is never bipartite except K2. Okay, Kn is never bipartite except K2. Okay, so why K2 is bipartite? So obvious, this is K2. I have told you just now. K2 is bipartite. And how K3s look like? K3 will be this. Okay, so it will never be bipartite because it is a 3 vertex. How K4 will look like? How K4 will look like? This. So let me draw it properly. How we have drawn K4? So we have taken K3 and then I have joined like this. This was K4. So in K4, obviously triangle is there. Triangle is odd length cycle. The moment you get odd length cycle, you will say no, it is not bipartite. How K5 will be drawn? K3. This is K4. Okay, and let me draw it properly. So K4, just take K4. K4 is having a triangle, na? K5, you will say like this, and so on. So every other say K3, K4, K5, K6 and so on, it will be having an odd length cycle, that is a triangle. So 3 length cycle will be there in every Kn for n greater than or equal to 3. So hence it will be never be bipartite. So I will say like this. So Kn for all n greater than or equal to 3 is never bipartite. Why? Because all will have triangle, that is 3 length cycle. Is it okay?
Yes, sir. Suppose if the drawing is as you gave the previous slide example.
Previous slide, yeah.
It was a rectangle. That is one, the last one.
So there is this one.
It is a bipartite.
Yes, it is a bipartite because no odd length cycle.
Yes, sir.
Yes. So you can take snapshot of this, and I will jump to the next slide. Okay. Next is complete bipartite graph. It is represented by Kmn. Okay. So Kn, that is complete graph of n vertices, and complete bipartite graph is represented by Kmn. Why Kmn? For m for the first set, n for the next set. Okay, so here m vertices and here n vertices. Okay, so G is Kmn if and only if every vertex in the first set U is adjacent to every other vertex in second set V. That is very obvious. See, what was complete graph of n vertices? Every vertex was adjacent to every other vertex, like this. So what will be complete bipartite graph of see Mn? So Mn I will say like this. Here I am having say m vertices, and here I am having say n vertices. So every vertex should be adjacent to all these, na? Are you getting it? So here also this will be like this. So it will be complete bipartite graph. Just like complete graph, we have complete bipartite. Any doubt?
No, sir.
Okay. So another definition is edge is present between two vertices x and y if and only if x belong to u and y belong to v. If and only if means both ways. So if x belong to u, y belong to v, there will be an edge. Okay, and there is an edge means x belong to u and y belong to v. I think you have got it. One and the same thing.
No, sir.
Any doubt here?
No, sir.
Okay, so this is very important example. This has been asked in GATE many times. Okay, and it has many applications. So what about this graph? How you can link this graph? So let me say you. So A, C, and E same. A, C, and E. These are this is an independent set because A, C, and E are not connected. BDF independent. This and this. So A is connected to BD and F. See this. A is connected to B, D, and F. A is connected to BDF. C is connected to again BDF. You can check it out.
Yes.
E is connected to again BDF. You can check it out.
Yes,
So what is this K33? Complete graph of complete bipartite graph 3 3. Are you getting it?
yes, sir.
Okay, so how K22 will look like? This. Okay, and how K11 will look like?
Straight.
Like this. And K11 is nothing but your what? K2. K, and it is nothing but Q1. Okay, and it is one regular with two vertices. One regular with
Two
two
vertices.
vertices. So I am just making these just to give you an idea. It is to make the set. That's it. Okay, it is not required. Are you getting it? Now graph is this only. है ना? So I have just made it to just give you clarity. This is U set, this is V set, and so on. Okay, yeah. So K22, K33, K11. I think if you want to say K13, how K13 will look like? 1 here and 3 here. So like this. That's it. So I think it's okay. Image is clear. Take snapshot. I will jump to the next slide.
Copied, sir.
Okay. So KMN is having how many edges? Very easy. How many edges will be there? So say this. Here M and here N. This is connected to all the M. This again all the N. So N plus N plus N. How many times? M times. So it will be N into M. Any doubt?
No, sir.
Take snapshot. I will jump to the next slide.
Okay, sir.
Okay, next. If complete bipartite graph is having n vertices, then maximum number of edges in it will be. If complete bipartite graph is having n vertices, so now they are not divided it into two sets. They are simply saying complete bipartite graph is having n vertices. Total we are having n. Then maximum number of edges they are asking. So for example, if you take n is equal to 6. So now they have not bifurcated. Are you getting it now? K33 or K24 or you can have K15 and so on like this. Are you getting it?
Yes, sir. Yes, sir.
So what will be our answer? So maximum number of edges, how many maximum number of edges? So first of all, you have to divide 6 into parts. So how 6 can be divided? So 6 can be divided like this: 1 5 2 4 3 3. Okay, now don't say 4 2, because 4 2 is 2 4 1 and the same thing only. So how many edges here? M into n were there, na? So it is nothing but your k15. This will be k24. This will be k33. So 2 into 4 8, 3 into 3 9. When maximum? 3 into 3. Okay, so 9. So similarly, if I say we are having say 7, how you will divide 7? 1 and 6, or 2 and 5, 3 and 4. Now don't say 4 3 and so on, because they will be repeated. So 1 into 6 6, 5 into 2 10, 3 into 4 12. So clearly 3 into 4 is the maximum. So now I will generalize the things. So if n is even, so when you will get maximum? K n by 2 comma n by 2, half half, divide half half. Are you getting it? So so n vertices were there, so divided it into half half. So for example 6, then 3 3 is giving maximum answer. 8 4 4 will give us maximum answer. Okay, then 10 5 5 will give maximum answer, and so on. Any doubt?
No, sir.
If you want, you can think like this: 8 2 4, sorry 2 7 6.
Sir, 8 1 7.
Sorry 1 and 7
2 6.
2 6 3 5 4 4.
4.
So 4 4 16, 5 3 15, 6 to the 12, and 7. What is maximum? 4 into 4. So divide it into half half. That is the best way. When n is odd, so you will take k n minus 1 by 2 and n plus 1 by 2, like this. Okay, so 7, so 3, so 7 minus 1 6, 6 by 2 is 3, and 7 plus 1 8 by 2 is 4. So this is the answer when n is odd.
Yes, sir.
If n is odd. So if complete bipartite graph is having n vertices, then maximum number of edges in it will be, so it depends. When n is even, you will say n square by 4 is the answer. And when n is odd, you will say n minus 1 into n plus 1 divided by 4. For odd. For even, this. Any doubt?
No, sir.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Okay. Next, chromatic number. So chromatic number, I am introducing a term. After introducing the term, then we will study chromatic number of all the graphs, like null graph, then cycle graph, regular graph, wheel graph, okay, hypercubes, and your bipartite. All these. Okay, so I have done till here. We have completed all the types of graphs. So total we have studied, I think so, 6 or 7 8 types of graph. Okay, rather 7. Bipartite and complete bipartite you can consider one only. Okay, bipartite, it's a subset of bipartite, that is complete bipartite. 7 types of graph we have done. So now I am introducing a term called chromatic number, and then we will study chromatic number of all the graphs one by one. So what is chromatic number? See this: minimum number of colors required to properly color the graph. What do you mean by properly color? Properly color means no two adjacent vertices can have same color. And what is chromatic number? Again and again I'm repeating: minimum number of colors. I'm not saying colors, I'm saying number of colors. And what is minimum? Kam se kam. Okay, minimum number of colors required to properly color the graph, that is known as chromatic number. See this, see the example. For example, you color this vertex by red. So the moment you color it by red, what you will say, now here you cannot take red, here also you cannot take, because all both are adjacent to this. Okay, properly color means no two adjacent vertices have same color. Red is not allowed. So can I give here green? Yes. So I will take here green. Now can I take here green? No, because it is adjacent. Can I take here red? No, because it is adjacent. So I will take here blue. So 3 colors are needed. Okay. So here how I will check? I will take here red. Now basic idea for to find the minimum chromatic number is you just give same color to all the non-adjacent vertices. What are the non-adjacent? See this. So you will take here red. Okay. Try to reuse. You consider them as rupees. Do not spend them unnecessarily. So red and red. Now you say, can I take it as red? No, because it is. So take green. Now you say here, come here. Can I take it green? Yes, definitely. First of all, see this. Can I take red? No, because they are adjacent. So can I take green? Yes, that's it. 2 colors are sufficient. Here 3 colors were sufficient. And what about this? So you can start with any vertex. Okay, whatever way you want, you can take. So for example, I can. Okay, and one more thing. You should start with that vertex which is having degree minimum. Okay, because if you start with that vertex, then maximum number of vertices can have same color. Okay, so here I will take red. The moment I take red, I will immediately take here red. Okay, now can I take here red? No.
Yes.
No doubt they are non-adjacent, but it is adjacent. Here red? No. Here red? No. Okay, so forget about this part. Come here. Can I take here red? Yes. Can I take here red? No. Can I take here red? No. So now you take another color. So if I take here say blue, if I take here blue, so immediately so are you getting it? So I'm taking new color at vertex having minimum degree minimum red. So I have taken all the reds. Now I will say blue. So here it is minimum degree. I will take blue, and then can I take any other blue? Yeah, this is blue. This is blue. Yes. Okay. Yeah. So now here, can I take here red, blue? No, green. I have to take another green. Here also green. So 3 is the answer. So simple.
Yes, sir.
Okay. So by common sense, I think by common sense you will be able to do it. No need to worry. And by the way, I will jump to this topic at end of the graph theory. When we will ending the graph theory, I will come back to it again, and I will tell you lots and lots of theorem related to chromatic number, and it is very important topic for GATE. Many questions have been asked from theorems also. So I will give you theorems and all when we are trying to complete this graph theory topic. The name of the topic will be graph numbers. We will study lots and lots of graph numbers, and in that topic I will give you idea of chromatic number. Okay, and many other numbers will be there. Okay, one by one we will study all the numbers. Don't worry. Okay, so we will study that. Okay, so in that we will study theorems, and there I will tell you the way to find the minimum chromatic number and so on. Sorry, a minimum number of colors to color the graph, properly color the graph. That is nothing but your chromatic number. Okay, so more precisely, chromatic number, more information I will give you in the topic graph number. That will be the last topic of your graph theory. Okay, here I'm just giving you the idea so that you get more clarity about the special graphs. Okay, chromatic number of special graphs. We are studying this topic. Okay, take snapshot. I will jump to the next slide. So here our aim is to study chromatic number of special graphs. I'm not digging deep into the chromatic number topic. Digging deep into chromatic number topic will be done in graph numbers. Here not. Okay, next. So first graph was null graph, phi of n. So for phi of n, I will say phi of 1 like this, phi of 2 is like this, phi of 3 is like this. What is the chromatic number? You give here red, 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 and so on. So only one color is needed because no vertices are adjacent. No problem. So kg for phi n is 1 for all n, and in fact this is the minimum possible kg. Kg is the representation of chromatic number. See this kg. Okay. Yes. So kg is minimum. Minimum kg is 1. Okay, and it is for phi n. So this is a very beautiful theorem. This has been asked in GATE. So kg is 1 if and only if g is phi of n. Okay, why? Because for null graph only kg will be 1. If it is not a null graph, then there will be at least one edge. The moment you get at least one edge, you will say this is red, so this cannot be red, this should be green. So minimum 2 colors are needed. So this is what I have written, because even if one edge is present, then kg will be at least 2. I have written with another color so that you get more clarity. At least 2, that is for sure. even if one edge is there, because the moment you get one edge, you will have to take two colors. Is it okay?
Sir.
Take snapshot. I will jump to the next slide.
Done, sir.
Next is regular graph. So what about regular graph? Zero regular. For zero regular, null graph only. So it will be 1. Okay. So this is zero regular example. Another zero regular is this. Another zero regular is this, and so on. So they are nothing but your phi of n. So chromatic number will be 1. For one regular, what will be the chromatic numbers? Red, green, red, green, red, green, and so on. Okay. So like this, are we getting it? So two regular. What about two regular? Two regular like this, or like this, and so on. So for two regular, so here chromatic number is 3. Here chromatic number is 2. I have just given you idea. Are you getting it? Red, red, green, green, and so on. So there is no direct formula for regular graph. Okay. So for zero regular 1, for one regular 2, that is for sure. For two regular, it's sometimes 3, sometimes 2, and so on. So you will it will be a bit difficult, and rather there is no formula. Then why we should dig deep into this topic? So if they give you any regular graph, you have to find it out. No way out. Okay. Yeah. Take snapshot. I will jump to the next slide.
Done, sir.
Hmm. Next is complete graph of n vertices kn. So k1, one chromatic number will be 1. That is nothing but your phi 1, and it is q0 also. No need to worry. So 1, k2, chromatic number 2. Why? Red and green. K3, chromatic number 3. Why? Red, green, blue. K4, chromatic number 4. Why? Because all are adjacent. Very simple. When all are adjacent, so you cannot reuse any color. Are you getting it? Red, green, blue, yellow. So 5. All these 5 are adjacent, so you cannot reuse. So chromatic number will be 5. So kg for kn is n, and it is the maximum possible kg. So you cannot have more than n. Chromatic number cannot be more than n. So how you have used how? So if more than n means what? You have given two colors to one vertex. That is not at all possible. Two color to one vertex, not at all possible. So one color to each and every vertex, and no reuse. That means complete graph. So maximum possible is n. Okay. Kg for kn is n, and it is the maximum possible kg, and range of kg is 1 to n. I think you have got it. 1 for null graph and n for complete graph. Take snapshot. I will jump to the next slide.
Yes, sir.
Next is cycle graph or CN. Here, what is the chromatic number? 3. Red, green, blue. Here, 2. Red, red, green, green. Here, see this. Red, red, red.
No.
Green, green. Oh, sorry. I have done some mistake.
Yes,
Yeah.
sir.
So this cannot be red, no? This is red, this is red. This cannot be red, this cannot be red, this cannot be red. So I will take blue. If this is blue, then this is blue. Okay. And then no way out. So I have to take another color, say green. So 3. Here, red, red, red. Then no other red. Then green, green, green. So 2.
Sir.
So now we have got the formula. So for Cn, if n is odd, 3. If n is even, 2. Okay.
Yes.
Take snapshot. I will jump to the next slide.
Done, sir.
Wheel graph WN.
Just a moment, sir.
Yeah.
The last slide.
Okay, last slide. Okay.
Done, sir.
WN. So wheel graph of n vertices. So minimum is W4. Na? W3 is not possible. Okay, W4 is possible. So how W4? C3 plus 1. So
Yes,
it is very simple. See this. Red, green, blue. Okay, and you have to give another color, that is yellow.
Yellow.
No way out. Okay, and in fact if you try to open it up, this is the beauty of graph theory. If you try to open it up, what it will look like? It will look like this. That is nothing but your complete graph of 4 vertices K4. You just take it outside, try to imagine, take it
Yes, sir.
outside.
Ah.
Okay, so you will get K4. So K4 you already know, 4 complete graph of 4 vertices. 4 is the chromatic number, I have told you. For Kn, n was the chromatic number. For Kn, n is the chromatic number. All vertices are adjacent, no way out. Okay, yeah, for W5. So how you will say? So see this. If I take here red, can I take here red? 100%. No need to worry. Why? Because they are non-adjacent. Take here red? No. Red here? No. Here red? No. So you will take here green. Here green. Now here you can take blue. So 3. Is it okay?
Yes, sir.
So now I have written a formula just to save the time. Kg for Wn. What is Kg for Wn? It is Kg for Cn minus 1 plus 1. Why? Because for W4 you have taken C3 na, and then you have added Y1 because this vertex will be adjacent to all the vertices. So for C3 it is nothing but your K3. For chromatic number was 3, so 3 plus 1 was 4. W5 C4 plus 1. For C4 you will take 2 colors and plus 1 color. Why 1 color extra? Because this is adjacent to all the vertices, so you cannot reuse any of the color, so you have to take another color, so it will be 3. Okay, so here we have got 3. Okay, for K5, so sorry, for W6. For W6, how W6 will look like? First of all you will make a pentagon, and then first of all see this. This is C5 na. C5 need 3 colors. We have just seen it. So
Yes,
now
sir.
I will take a middle vertex. So it is adjacent to all the vertices. So no way out na. So you have to give another color. So that's why I will take C5 plus 1. For W6 I will take C5 plus 1. So C5 is 3. Rather I should say like this. Kg for C5. That will be 3. And plus 1 extra. So it will be 4. So Kg for Cn minus 1 plus 1. Kg for Wn is Kg for Cn minus 1 plus 1.
Yes, sir.
Take snapshot. I will jump to the next slide. Okay. So I think time is up. So just give me 1 or 2 minutes. No, actually many slides are left. Should I complete these?
Sir.
Okay. So just I will take maximum 3-4 minutes. So please bear with me.
Yeah,
Okay. Qn, Q0. It will be 1. No problem. Q1. It will be 2. No problem. Q2. It will be 2. No problem. Why? Because it is C4.
Yes, sir.
C4 na 2. So for Q3. So see this. Red. So this is adjacent, this is adjacent, this is also adjacent, so do not take it. So this is red. So for red, this is adjacent, and you can take here red also. Okay, these were non-adjacent. You pick this, you take it green. The moment you take it as green, you can take this as green, you cannot take it as green, and you can take this as green also. Okay, yes. So so now these two are left out, so you have to take here blue and here also blue. You can check it out. Any doubt here?
Yeah, sir. The green which you have taken inside here.
This one?
All right, sir. Yes, it can be.
Yeah. So 3 is the answer. Okay.
Yes.
So let me give you the formula. So for Qn, Kg is 1 if and only if n is 0. Kg is 2 if and only if n is greater than equal to 1. Kg is equal to 2 if and only if n is greater than equal to 1. So yeah, actually I have done some mistake. Yes, it should come out to be 2. So this, yeah, why I have taken it as red? Why cannot I can take it as red?
Sir.
This is red. Okay. and this can be
Here
green.
it can be green. Huh, sir.
2. Only 2 are needed. Yes, so kg for qn, kg is 1 if and only if n is 0, and kg is equal to 2 if and only if n is greater than equal to 1. So for q1, q2, q3 and so on, for everyone it will be 2 only. Kg will be 2, and for 0 it will be 1. Okay, so I think you have got it. So proof, qn is bipartite if and only if n is greater than equal to 1, because no odd length cycle. Okay, so and every bipartite graph is having chromatic number 2. That is very obvious. See this. If we have a bipartite graph, forget about simple, you take complete, no problem to me, complete. Okay, so since all these are non-adjacent, you take them as red. So they are also non-adjacent. So this and
Yes.
these are adjacent. You cannot take red, you can take green. That's it.
Yes, sir.
So every bipartite graph chromatic number is 2. Very beautiful theorem. Okay, so q1 is bipartite if and only if n is greater than or equal to 1, because no odd length cycle. Here there is no odd length cycle, you can check it out. See, for how you will check bipartite, there should be no odd length cycle. If there is odd length cycle like this or like this, you will never say it is bipartite. You will say it is not bipartite. Now everywhere, see this, here cube na 4 length cycle, there is no odd length cycle, no odd length cycle, no odd length cycle, and so on. So every q1 is bipartite except q0. Why? Because it is only one vertex. So
Yes, sir.
chromatic number will be 2. No problem. Okay. Yes. So kg is 2 for n greater than equal to 1, and kg is equal to 1 if n is equal to 0. So you can take snapshot. I will jump to the next slide.
That's all.
Okay. Bipartite. If bipartite graph is phi of n, then kg is 1, else kg is 2. I have just shown you the proof. Okay. When it is a null graph, it will be 1. Kg will be 1. Say this is a bipartite graph. So kg is 1. Okay. This is bipartite graph. 3 vertices now. So you take them like this. Okay. So kg is 1 because there is no edge at all. And when there will be edges, so it will be 2. Any doubt?
No, sir. Understood.
Okay, take snapshot. I will jump to the next slide.
Done, sir.
Next, KMN, again KG2. I have just proven you. So you take like this. Red, green, 2. No problem. That's it. Done. Okay, so we have completed the chromatic number. Next will be diameter and all. We will study that. No problem. So in the next class, we will resume from here itself. So we will introduce terms, and after introducing the term, and then I will show you for all the graphs. Okay, about null graph, about wheel graph, and so on. Okay, then.
This Sunday is a holiday, it seems, sir.
The sir has told you?
Sir told us. Like
Okay.
when I interacted with him, if there is any class, we can have on Sunday.
Okay. So Sunday there will be
class.
no, but sir has said me on Sunday I have a class from 1 to 3.
But it was not there in the timetable. So.
Okay, so I will confirm that with sir. So but tomorrow is Saturday, na? Saturday I am having class with you from 5:30 to 7:30. Computer networks.
Okay, sir.
Yeah, Saturday, and then I will get back to you about the Sunday. So you are saying on Sunday there is no class?
In timetable, it was not given class. Sir told only Sunday is a holiday because they have not mentioned the Wednesday as well as Friday. When I inquired about it, sir said only Sunday is a holiday. Other days we'll have discrete mathematics. As today was also a holiday in the timetable, but we have class.
Okay, so I think I should take. I think there will be 2 classes on Sunday for me because of the previous our syllabus is lagging. Na? That's why. I will talk to sir and then I will let you know. Okay.
Sir.
Okay then. Okay. Good night. Okay.
Thank you, sir.
Okay. Good night.